Allison, Duru Ahanotu, and Professor Tse, Professor Fehling, Professor Jucker, and Professor
Duvalier.
I'm sorry, I call Mr. Duvalier. So
That's
Mary is your first name.
That's right.
It wasn't a comma there. You had a comma there, so
Easier to
pronounce. Duvalier, Mary, Professor Duvalier are the examining committee. I am the university chair, Robert McGinn. I'm not obliged to take a substantive role, more like a traffic cop in the proceedings. The usual scenario is for the candidate to make a 45-minute presentation, followed by a brief break, then an opportunity for each one of the committee members to examine the candidate for approximately 15 minutes, and then a free-for-all after that. Is that agreeable to all? Okay. Duru, could you begin your presentation?
Okay, thank you, Professor McGinn. Hello everyone, my name is Duru Ahanotu, and the title of today's talk is Modeling Production Workers as Innovators.
You got focus.
Oh, whoops. That was already focused. Sorry about that.
Can you change the notes? Yeah. Okay, good.
Okay, sorry about that.
Just got too excited.
Okay, so again, my name is Duru Ahanotu, and the title of today's talk is Modeling Production Workers as Innovators, a dynamic simulation and field study of knowledge development in manufacturing. Now the presentation outline is very straightforward. We're going to first define the problem, go through this dynamic simulation model and the results, and then finally discuss the results from the field study or the practical implications of the conceptual concept, the conceptual theory that we'll discuss. So let's go ahead into the problem definition. First, a little bit of background and motivation. In 1990-91, Advanced Micro Devices, or AMD, decided to establish what's called a knowledge-based workforce. They're a leader in such practices, at least at certain of their plants, but they still seek to better manage the boundaries that define engineering work and production work. Finally, what they've been missing is a formal recognition of a differentiated, innovative ability amongst their production workers. And what they've needed is an analytical and practical framework and an evaluation techniques for the different strategic alternatives. So what we're going to do is try to provide this inclusion of production workers in innovative processes in production. So our primary hypothesis that we will propose here today is very simple and straightforward, that we can indeed improve the performance of manufacturers by formally involving production workers in processes of innovation. And this model is most relevant where market conditions or technological imperatives compel innovation. And we will characterize this strategy as knowledge development, or KD. So there are a few questions that we must answer to attack this hypothesis. The hypothesis is simple, but attacking it is pretty complex. First of all, how variable are the abilities to innovate amongst production workers? To what extent can production workers participate in innovation? Yes?
Are you going to give some background?
Background to?
The last slide had a hypothesis on it that I think people have tested in a number of places.
You mean in terms of
Empirically,
literature?
at least.
Yeah, throughout the talk I'll refer to different previous researchers.
Okay.
Are there different types of innovating production workers? And how can we rank the different strategies of knowledge development for using and promoting these abilities? And so what we're basically looking at is in the traditional conventional model, there's a bipolar concept that engineers are on one end of the spectrum of innovative ability and production workers on the other. And what we're going to propose is there's actually a distribution over which we can identify a different variation of production workers' innovative ability, and we will propose that there are actually 4 different types of production workers that constitute this variation or this distribution. So how is this variability relevant to production processes? Well, we define it by looking at continuous improvement and innovation. Basically, continuous improvement incrementally adjusts a single process state. It's dominated by production workers in the conventional model, and it's bounded by processes that are related to the conventional learning curve. Innovation, on the other hand, leads to a new process state, indexed by J, with transition probability Q, and it's traditionally or conventionally modeled as being dominated by engineering, what we'll call the SDK, sources of design knowledge. And innovation now relaxes the bounds on continuous improvement. And sort of the previous researchers in this area, Dutton and Thomas provided a good conceptual framework for this problem. Leonard Barton provided certain pieces of it and was one of the first to identify practical implications of this differentiation. And Young and Solow were some of the first to provide sort of an analytical framework, and their particular emphasis was on a macroeconomic model. And so again, to emphasize graphically what we mean between continuous improvement and innovation is that continuous improvement, again, is the incremental adjustment of a single process state indexed by J, and innovation is the transition from one process state to another one. And typically in an enlightened manufacturing companies, production workers dominate this process, engineers dominate in the innovation process. So now then, the resources in an organization are finite. So we must balance continuous improvement and innovation. And this is related to a very traditional concept of exploitation versus exploration, where we're trying to balance our resources between living off of today's wealth and developing future wealth generating capabilities. So in terms of production, what we're talking about is, do we want to focus on continuous improvement or do we want to focus on innovation? Again, the standard resolution that I'm proposing is that production workers create, or they focus on continuous improvement, and engineers and professionals innovate. Our proposed resolution is a more knowledge-oriented expansion of production work. And in organizational theory, this type of expansion is called empowerment. And these three tasks that we're going to expand across are called operations, which is our basic standard process of material transformation, experimentation, which is the intentional exploration apart from operations, and then absorption, which is any generic collection of knowledge acquisition processes that are also defined separate from operations and experimentation, and usually in collaboration with the SDK, or the sources of design knowledge. So now we need to take these tasks and distribute them amongst the different production workers. And what we are proposing is that there are what we call different cohorts of production workers, and there are 4 of them. The first one is defined as the core. The core is the nexus of the knowledge and production system. They are the center of the production workforce. Aspirants, in a sense, aspire to get up to the core level. They are initiators and they're proactive. Reservists represent the dormant potential of innovation in the production workforce. And they typically only innovate in times of organizational crises. And then finally, we have the sustainers, which represent the unused innovative potential of the system, and typically they only focus on existing production. Now, we should note that this does not imply any sense of differentiated productive ability. This only defines differentiated innovative ability. So now we're going to take these definitions and present a targeted strategy of knowledge development. We're going to allocate these 4 tasks of operations, experimentation, and absorption, customize it by the different cohorts, and then take this model, align the cohort migration, that is, the migration of production workers from one cohort into another one, and align it to our overall manufacturing strategy.
So those 4 cohorts, as you go from top to bottom, are less innovative.
Right.
Okay. Describe the difference between core and aspirants in terms of innovation. First, let me see if I got it this far.
Okay.
Sustainers don't innovate. Reservists innovate only in crisis.
Right.
What aspirants do and what do core people do?
Right. I'll attack that in more detail later on, but basically think of this, these production workers are more established in the production system, whereas aspirants will largely consist of, say, for instance, novices, or people whose knowledge base isn't quite up to speed yet to match up to the core.
But that doesn't sound like a difference based on different degrees of innovation. It's a difference, but not regarding innovation.
Right, well, I think it'll be clearer when I go through the rest of the model. Okay, so now that we've defined the problem, let's go through an overview of how this is all put together in terms of our dynamic simulation model, and then discuss some of the results. So here's a block model of what we call now an integrated knowledge-based theory of production work. And let's first of all start here in the top left corner. This represents the SDK, or the sources of design knowledge, and their primary role, we're going to assume, is to create innovation in the production system. And the only thing that may affect the growth of their innovative ability is the amount of time they spend on collaborating with the production workers in this absorption task. The production workers are divided into these 4 different cohorts, and they apply these 3 different tasks: operations, experimentation, and absorption. Each one of these has an effect on the production workers' innovative ability. Operations, on the other hand, may have a positive or negative influence, and this will define the different cohorts, and particularly differentiate the core from the aspirants and sustainers from the reservists. Here we have an adaptive learning model. This is more traditional in terms of production learning. We assume that system failures are Poisson distributed. Every time a system failure occurs, we respond to it. Our problem-solving initiative increases our stock of knowledge, and as we increase the stock of knowledge, we reduce then the frequency of the occurrence of system failures. So again, this represents a more traditional adaptive learning process, or continuous improvement. And what we presume is that both continuous improvement and innovation decrease costs, increase our production rate, and we build a stylized benefit model where market price is declining over time that motivates innovation in the company. And the stylized benefit model will allow us then to rank order different strategies or decision strategies of how to allocate these different tasks to our different cohorts of production workers. So what we're going to do, obviously it's a pretty complex system, we're going to de-emphasize the mathematical structure and focus in on a standard format of zeroing in on a particular part of the block model and then showing a graph to describe the behavior of the system. So again, this is the SDK, the sources of design knowledge. Their primary role is to concentrate on innovation in the production system. And they have a characteristic growth in innovative ability where we define the probability of innovation as the innovative ability. We model it as a logistic growth equation, which is analogous to models of diffusion of innovation. And we also assume that it's aggregative, so we can consider it as a group. It's instantaneous, so when we invest resources, we immediately see the outcome. And it's transferable, so that once we build it in one person, it's immediately transferable to all. Now we will take this logistic model and we will extrapolate it now over to the production workers. So again, as a quick reminder, production workers, through operations, they can either positively or negatively influence their innovative ability. And what we assume is that in the system, there are these asymptotes that define different regions of innovative ability. And at the extremes at the top and bottom, the decline or the influence is negative, and in the middle it's positive. This maps into our cohort model as so. What we assume is that this Q sub H sort of defines the maximum sustainable level of innovation in our production system. But we define the core as being well established enough that they are actually above this level. And without any non-production tasks of experimentation or absorption, their innovative ability will decline over time. Whereas aspirants start below this level, over time they will gradually increase to the top sustainable level of innovation in our production system. Reservists, since they only innovate in times of crises, sort of drift along to a lower level, Q sub M. And then finally, sustainers don't really build their innovation abilities at all, and they will decline towards zero. Now that we have this model of just the influence of operations on innovative ability, once we add in the two non-production tasks of experimentation and absorption.
Okay, hold on, Duru.
Yes.
So I think you just, on that last slide, answered my question by saying that you assume more innovation in the core than in aspirants.
Right.
Okay.
Yeah, and I validate this through the field study at the end.
Okay.
So now what we do is we take an aggregation technique, and here is the graph that represents the aggregation of the innovative ability of production workers. Notice that it's very flat and it rises very slowly. Once we add in these two non-production tasks of experimentation and absorption, we now have what we just call a near optimal graph, where it rises, the innovative ability rises faster and to a higher level. And we call it near optimal because it's not possible to prove optimization, but we can provide attractive, different strategic options. So now I'll just indulge you for a minute to just examine the mathematical structure just for presentation purposes. Again, here's the SDK, the source of design knowledge. We model the growth rate of innovation as the current level of innovative ability times the remaining potential. The production workers on the operations side, again, is also a logistic. It's more complicated because we divide it across the different cohorts. Here's our decision variable gamma, which defines our allocation of tasks. We assume that the growth of innovation in absorption and experimentation is exponential growth. And then finally, we have our aggregation technique, which presumes that when we try to add together the innovative ability of our different organizational agents, we weighted by a presumed productive ability of the cohorts and also the percentage of the total population of the production workers, and then we aggregate all together the innovative ability of the SDK, of the source of design knowledge, and of the production workers to come up with a total measure of innovative ability in the system. So now we take this definition and combine it with continuous improvement. And again, just as a simple, quick reminder, we model continuous improvement as an adaptive learning process where we're responding to system failures, and we assume that the rate increase of knowledge is directly proportional to the rate of decrease of cost and the rate of increase in production rate. And innovative ability also has some sort of influence on these two manufacturing metrics. Well, how does this work? Well, here's our model of continuous improvement. We assume that because of the fact that it's an adaptive learning process, it will increase just like a learning curve, and our stock of knowledge will come to some maximum level. Now, how do we define innovation in this model? Well, we can take Roger Bowen's stages of knowledge as an analogy. Basically, as we're continuously improving the production system, we're gaining more and more control over the production process. But when innovation occurs, we lose some of our control in the production process. So we simply model this then as a step backwards in our knowledge stock. We lose some of our previous knowledge. If we think about this in the limit, if innovation carries over our complete stock of knowledge from the last process state, it means then that this curve will just continue on as it was before, and we don't have an innovation, we have a continuous improvement.
Sorry for all the questions.
No problem.
And they're still clarifying. Are you going to tell us what determines the size of that increment downward?
This size here?
Yeah.
I used an empirical estimate from my field study, but I won't go into the details in this talk about how to determine that.
We'll talk later.
Okay. So again, I will just indulge you for a few seconds to just take a quick review of the mathematical structure behind this. Here we have our adaptive learning process where we model the rate of increase of the knowledge stock times one of our decision parameters, which is the amount of intensity of operations, times the random variant, which is the number of failures that occur at a given time, times what we call our difficulty of production learning, or tacitness. This models the decrease in the arrival rate of failures. This says now that as our arrival rate of failures goes to 0, our knowledge stock reaches its maximum level, K hat. And then finally, here's a simple relation for our knowledge stock in the current or in the next process state is equal to some fraction of our knowledge stock in the previous process state. So now we put this all together to take a look at our stylized benefit model, and we index this again by our different process states, J. And if we look at one particular process, this curve here is our decline in unit cost. So again, notice how continuous improvement and innovation work together. As we're learning through this, as we're doing our production learning, costs decline, but there's a limit, there's a total limit to the amount of cost declines we can realize in production. Once innovation occurs, at this point, we now reduce that limit over which we can reduce costs, and now we open up more opportunities for continuous improvement. So now, since our market price is declining over time, this allows us to maintain a viable production system over time. And this just represents the increase in discounted benefit. So now it's pretty difficult to show how graphically how changing all of our decision parameters over 4 different cohorts, how it looks. So we're going to just focus in, just for presentation purposes only, look at how the system performs when we increase the amount of experimentation of the core. And we find that they have the most strategic leverage in the system. This thick graph here shows that as we increase experimentation initially, we drift upwards as a non-convex system, so there are a few peaks in here. And then finally we give them so much experimentation responsibility that we detract from our productive abilities. And as we do that, we go all the way to the end here, and finally there's an anomalous blip here where now the core are pretty much like engineers, and the system benefits increase. So again, this is sort of an anomaly of the system. And this now represents, again, if you remember this bipolar model of production workers and engineers, this represents the core becoming more and more like engineers. And just to confirm that the system is getting more and more innovative, this curve here represents an increase in the number of process states we're able to create through the experimentation task. So that again was just for presentation purposes to show how this system behaves. So let's take a look at the results in terms of the different strategies that we can apply to our task allocation. I labeled them as LA through LD. LA is full production, and we find that it underperforms all of our strategies. And we call them from balanced to medium to aggressive, depending upon how much resources we commit to our innovative process. And essentially what happens here, at the balanced strategy, all of the cohorts of production workers have a pretty relative balance in terms of the resources given to them for innovation. But as we move down into more aggressive strategies, we actually start to focus more on innovative ability of the core. And the result here is just shown in these three different cases, the difference in performance from full production. And we find that the balanced one performs a little bit under the other two. The aggressive strategy is just below the medium strategy. Now the magnitude seems small, but this is because we took conservative estimates of our parameters. So it's encouraging that we still were able to provide an increase in performance, even though we did a very conservative model. So what we're most interested in is the rank order of the different strategies. So if we look at rank order, LC is number 1, LD number 2, LB number 3. And of course our model does not include other benefits to innovation, such as higher product quality and faster response times, better competitive response.
A couple of questions now. What is medium strategy?
Medium strategy.
Balanced.
Right. Oh, right. Balanced strategy. We're talking about balance across the different 4 cohorts. Okay. So from balanced to more medium to aggressive.
What does medium mean?
Medium means that we now have increased slightly the commitment to innovation for the cohort. So as we move down here, we're committing more and more resources to innovation and taking it from production.
Now these are the differences in heights between these two regimens.
Right. What I did is
performance differences.
right. I made a very conservative estimation of my understanding of AMD's production system from the field study, and I wasn't able to obtain estimates of all parameters, but
So these are empirically grounded bar graphs.
right, partially empirically grounded, because for the parameters that I was not able to get direct estimates of, we find that the system is not sensitive to those parameters. Okay, now, as I stated, through our sensitivity analysis, the system was actually very robust, except for in 2 key strategic areas. The first one is this concept of the difficulty of production learning, or the tacitness of learning in the production system. And what we find is that as it gets more and more difficult to do this adaptive learning process, we have to commit more and more resources to innovation. So here are different cases, LB through LD, and notice we go from here to very difficult production learning. The rank order takes a complete switch, and all of our strategies now underperform the full production case. And why does this happen? If we remember again in our model of continuous improvement and innovation, continuous improvement, if it's very difficult to learn in production, our continuous improvement curve is only going to get up to a very low level. And when innovation occurs and we take that step backwards, innovation loses some of its impact. So as it becomes harder and harder to climb this continuous improvement curve, then we have to move more and more resources to full production, or to production to the point where, when it's very difficult, now full production becomes actually the best strategy. Do not commit any more resources to innovation. And then the next area is this migration of cohorts. And this migration of cohorts can also change strategy. And what I mean by migration is now we're allowing the different production workers to move into different cohorts of production. So again, we have the core, they go to a steady state. In fact, all of our different cohorts move to a steady state. We define a migration event as an arbitrary collection of different processes. We also assume a static allocation strategy such that once we set the strategy in terms of the allocation of tasks across the different cohorts, we cannot change them. And an intrinsic desire to migrate, so that everybody, if they're given the opportunity, will migrate to higher and higher innovative abilities. So this is the full production case, LA. And notice that the core reaches a certain level that is lower than the other 3 strategies that we use, where pretty much everybody moves into the core. So this is a little less of a conservative assumption, but there's a whole wide range of migration strategies we can apply. This is just one of them. And what happens in this case, again, if we assume a static allocation strategy, meaning that once we set our allocation of tasks, we cannot change them, now the balance strategy performs the best. Because now we have a nice, even commitment of production versus innovation. And now our most aggressive strategy underperforms. And this happens because, remember, the definition of balanced, medium, and aggressive strategy was that as we get more and more aggressive, we're assigning more innovation to the core. That means less production ability. So as more people move into the core, obviously we will have less commitment to production, and sooner or later we will deteriorate or degrade our performance. So let's take a quick review of where we've been in terms of this integrated knowledge-based theory of production work. We looked at the influence on innovative ability of the SDK, the source of design knowledge. We looked at the 3 tasks across the different 4 cohorts of production workers, how it affects innovative ability, how it affects this continuous improvement process, which is modeled, again, as an adaptive learning process, a failure-based learning process. Continuous improvement is modeled as being, or the accumulation of knowledge is modeled as directly proportional to our decline in cost, increase in production rate. We used a stylized benefit model where market price is declining over time, and this benefit model allowed us to rank order the different allocation of tasks across our cohorts. So now that we've done all this analytical work, let's take a look at some of the implications of the field study. First of all, just let you review very quickly a list of companies that I looked at to come up with these concepts, just for a few seconds. And the one to take particular note of is Advanced Micro Devices, where I did an actual observation study where I interviewed the different organizational agents in production. So let's take a quick overview of this field study. The goals of the field study were to develop, link, and justify the analytical and theoretical models. And most importantly, we wanted to validate this characterization of cohorts. Do they indeed exist? And if they exist, how do we identify them? And for this talk today, we will concentrate on this part of the model, or this part of the field study. The size of the study included 123 hours of interviews, generated about 940 pages of notes, spanned 4 months, 79 production workers, which represented about 1/3 of the whole production force, all of their frontline managers, about half of their production engineers, and all of their upper management in the production process. And our method of study was a 1-hour semi-structured interview. So let's first of all take a look at what is the infrastructure for innovation and production at this particular site. Well, first of all, it was very informal. And we found that there was a large variety in styles and in methods of management. That there was little consistency in their knowledge development philosophy, and yet they were able to establish a strong culture of continuous improvement. And the way they did this is through what I would call sort of a tendency towards an autonomous empowerment. And again, remember, empowerment is this expansion of tasks from operations into experimentation and absorption. And autonomous meaning that production workers in the system are highly trusted to run production and to do continuous improvement, but they are largely on their own to execute this knowledge development strategy. And similarly, engineers also do knowledge development informally, according to their own personal preference. And the implications that I found out of this whole infrastructure for innovation is that one of the practical methods for implementing a formal knowledge development strategy is to have the frontline managers coordinate the process, have engineers implement the process, and have upper management provide the resources. And this is a more contextual to manufacturing, and more integrative than other models that have been proposed on specific portions of the production learning process.
That's a conclusion you come to.
Right.
From what did you derive that conclusion?
I'll get into some of those slides in a
Can
few
you tell us what
seconds.
you mean by more contextual for manufacturing?
Oh, contextual meaning that, for instance, Nonaka and Takeuchi, they have what they call the knowledge crew, which has a similar format to this, but because they only concentrate on generic product development, they never posit or propose a specific role for engineers or production workers in the process. So that's what I mean by more contextual to manufacturing, that it's more specific to the manufacturing environment. This whole knowledge-based work, this theory of knowledge-based work. And whereas in these other two models, Modi and Adler and Clark, they specifically only looked at the interaction between production workers and engineers, but only in terms of the continuous improvement process, but not the entire integrated model that we're looking at.
So rather than waiting, why don't you summarize the answer to my question?
Repeat it.
The question was, there's a conclusion.
Right.
From what's your logic for deriving that conclusion?
Oh, okay. The logic here is that under their more informal infrastructure, or what's often assumed is that frontline managers are the ones who lead the process. But what I found is that frontline managers, because it's an empowered workforce where we expand the task, we increase responsibilities to all our different members of the production workforce, they don't have the time nor the technical expertise to implement this knowledge development strategy. It's key for engineers to implement it because they have the conceptual and the theoretical knowledge required to promote innovation in the process. But if they're only executing knowledge development according to their personal preference, we're going to underutilize then the innovative potential of production workers. And then upper management just provides the resources, which is similar to some of the conclusions in Nanaka and Takeuchi. So now we're putting all these different pieces together in one integrated model.
You know what I'm having difficulty with? I'm trying to map this into reality, right?
Right.
And some of these categories are just very large. I mean, there's different kinds of engineers whose engineering knowledge spans different kinds of knowledge.
Right.
Okay. And again, I'm going to speak very practically about this. You've got Joe out there on the assembly line. Joe's been working for years. And Joe has been working with a particular set of machines, let's say. You got Sam up there as an engineer who is, if he's a design engineer, for example, product design engineer, he is highly likely to have very little understanding of what Joe knows about how to use those machines, including in innovative ways.
Right.
Okay. If he's a process engineer, it might be a little different. Okay. So you see what I'm driving at? You've lumped together some things that could have vast differences in the conclusion that you're reaching, because Sam's ability, the guy that was the design engineer, his ability to coordinate this process of knowledge discovery and so forth could be extremely poor.
Right.
Now, this isn't coming out of any nitpicking about your model. This is coming out, this is addressing modeling assumptions that I'm trying to understand.
Right, and I guess I don't address those specifically here, but I suggest that this differentiated model of engineering resources as an avenue for future research, and I sort of suggest how we can attack just that similar problem that you mentioned. But indeed, we were focusing here on production workers, so we're looking at the differentiated model of production workers and lumping the engineers together so that we can focus and scope the work down to a specific, specific area.
Well, we can come back to that.
Okay. So next, let's take a look at then how we determine these different cohorts of production. And the importance here is to develop and test a method for identifying these cohorts in a practical setting. And the result was that indeed these cohorts seem to exist, and AMD's particular production workers have high innovative potential based upon the allocation of cohorts. We validated our method of identifying the cohorts and found that cohorts do have a high explanatory power to explain innovation in production. And what I did was take out of the interviews, I took two big categories called work approach and work impression. Work approach is basically how does a production worker approach their work? Are they just content with whatever setup of tasks they're given? Or on the other extreme, are they initiators? Do they go out, volunteer for projects, ask for different types of work? Or are they in this category called stay busy, which is on the surface, these people may look like they have a lot of initiative, but actually their motivation is only to stay busy, to fill up the work hours, just to prevent themselves from getting bored. And then this other big category called work impression, we can look at production workers, whether they consider their work as routine, I'm just doing standard operation tasks, I follow steps 1, 2, 3, or do I think of my work as being very challenging? That is, I'm learning something every day, and every day is a learning opportunity. We take these two categories and developed a heuristic to map them into these different production worker cohorts. I won't go through the details of the heuristic now, but basically we found that indeed there's a nice profile of cohorts at AMD that suggests that they have high innovative potential, particularly in the number of reservists that they have in the production process. So let's look at, we examined many different indicators of how the cohorts explain innovation, and we're going to just take a look at a few here, just one or two. And what we did here is that we asked production workers, which types of work do you prefer the most? Development work or production work? Development work has more of the engineering type of work, has more opportunities for innovation, and it has more experimentation types of tasks. If we look at if we look at these bars, the black bar represents the percentage of production workers that prefer development work. And as we would expect from our model, we go from a high rate to a low rate from core to sustainer. Going the other way, in terms of preferences for production, we have a higher rate of sustainers and going down lower towards the other side, to the core. And what surprised me in our result in the study is the amount of people that actually preferred neither development or production work. And what we will find, what I found is that this diversity of learning sources, that is, giving production workers the opportunity to learn from development and production type work, is actually very important to knowledge development. And this is shown in a few other examples of companies that I won't specifically go into now, but this is just for quick reference. So again, this diversity of learning sources, the development type work, which consists of more experimentation, more absorption, versus production, is very important to knowledge development.
I'm sorry. I really want to make sure I'm understanding
Okay.
this. You had quickly gone over something, maybe you explained this and I'm just being dense, but
Okay.
it seems, if I'm going to make sense out of this, I really want to know what how you operationalized assigning people to these. You said it in a previous slide very quickly,
Okay. Well,
that you
okay.
validated your cohort.
Right.
You know, your model that there are these 4 cohorts. Well, what I'm interested in now is, empirically, what did you use to determine a priori that somebody would count as being in the core or one of the others?
Oh, you mean
Okay.
a priori? No,
A priori,
actually,
what's your
right.
criterion for deciding which cohort they're in? And what kind of data did you use to determine that?
Right.
So I'm asking an operationalization question.
Okay. Yeah, there's a lot of, I guess, mechanical details in answering that question, but
You just gloss it because you've only got 45 minutes.
right.
You know.
Yeah. Basically, what I did was, from the different questions, I asked a series of 20 questions of the production workers. And so from their responses basically to how they thought of learning opportunities in production, how they view their work, these kind of questions to see what are their daily tasks, how do they approach their work, whether they think of it as routine and challenging. I came up with these 2 metrics. And then I assumed, for instance, I'll give you one example, that the core will always be in this work impression that they consider their work as challenging and that they're initiators. That will automatically determine, this will automatically determine either the core or the aspirants. A sustainer will always be someone who's very content with their approach to their work and they consider their work very routine. That's always going to be a sustainer. So that's sort of how I operationalize these definitions.
Okay.
But there's a series of 20 questions or more that I asked of every interviewee to come to these bigger categories.
Okay.
Okay. So let's take a look at the expanded tasks that we proposed earlier. First of all, we find that AMD is actually underutilizing experimentation in their production system. If we look at this white bar, this represents the amount of experimentation. This is a histogram. This represents the amount of experimentation that the different production workers or technicians are doing. But if we control for the amount of assigned experimentation, we find that very few production workers are actually doing original investigation, which would qualify for experimentation in our model. But the implication for this, actually, there is a positive implication for this, which is they have a unique opportunity having all of this high rate of assigned experimentation. So what it says is that we can actually use these experiments to teach more theoretical and conceptual knowledge that's required to promote innovation in production. Now, if we look at the absorption side, or the collaboration of how technical improvements or innovation occurs in the production system, this category is a little bit more difficult because I only had an hour to interview someone, so it's very complicated to explain to them the difference between a continuous improvement and an innovation. So what I did was I just lumped all technical improvements together and I asked them, with whom do you collaborate on these technical improvements? We're only going to concentrate on 2 of these bars. The white bar indicates the percentage of production workers who said that they collaborate on technical improvements with other technicians, engineers, and facilitators, or frontline management. And as we expect, sustainers have a very high rate of collaboration. That is, whenever they're involved in technical improvements, it's always in a group. And then we go down, we decline in this rate as we go towards the core. This black bar is very interesting in terms of these are the percentage of production workers that claim they independently came up with technical improvements. And particularly note that the aspirants have a higher rate than all the other cohorts. And what this means is that this high rate of initiative, they're so proactive that when projects come up that no one else wants to do, they're the first ones to volunteer. So they step forward a lot to take on projects that maybe other people find too difficult or it interferes with their production operations tasks too much. So the results and implications for this is that those with the most capability and or resources tend to innovate independently, and that the core may indeed act as the nexus for the production system in terms of innovative ability.
And these were rating scale data. I mean, these people were these are self-reported.
So all data is self-reported.
Did you get any data to try, any observational data to try to corroborate?
Unfortunately, their data tracking system was very difficult. I'm going to suggest as future research to do a longitudinal empirical investigation where you look specifically at the mechanics.
Because I would expect the folks that are the least empowered workers, and I mean the more traditional sense of empowerment, the folks on the line, I would really not be surprised to see them claim that everything that was good came out of collaboration, especially with their bosses.
Oh, okay.
Okay. I mean, there's some really interesting confounding factors to worry about in accepting at face value this kind of report data, it seems to me.
Right, and that was,
You know,
yeah, that's why I did conservative estimates, because all of this data came out of self-reports.
But it might also be a function of how private the communication was, and whether there was anonymity in the reportage.
Oh, there's a whole bunch of things associated, but you know, here's a simple one, there's a power issue here. I mean, we've got an ethos in this culture of individuality, and I would expect engineers, especially senior people, to say that anything good that came out, they did on their own. I wouldn't be at all surprised by that. And we've got an ethos of power that would lead me to not at all be surprised that people who were at the bottom of the food chain would say that anything they did was due to the good work they did with their workers or with their bosses or anything, which is a way of distributing the risk, among other things. So it's an example of a concern that I want to discuss with you later.
Right, okay, no problem. Okay, so now I'm going to try to summarize these field results and include some that I wasn't able to show graphically. First of all, we found that production cohorts do seem to exist, and they do seem to explain most sources of innovation in the production system. Engineers play an essential role in all aspects of knowledge development for production workers, but of course the caveat here again is that they do it only according to their personal preferences. The third point is that knowledge development at AMD is informal, and they integrate it into work as a Slack activity, and typically it's done by those who are most capable of comprehending the available opportunities for innovation. And then lastly, the emphasis on continuous improvement, I found, is very important for building a strong foundation for building capabilities of innovation. And
I think
yes.
I'd like to see just a brief clarification of number one. I have a slight problem with number two. That is, what does it mean to say that production cohorts can explain sources of innovation? What is that? I need a bit of clarification. On what
right.
that means.
What I didn't show in these graphics is that I looked at different ways of explaining it. For instance, task domain, their position. You know, task domain meaning what are their operational responsibilities, and I looked at which category, cohorts or these other things, whether on the night shift, on the day shift, which one of these would explain best, creates the most differentiation in these indicators of innovation in the production system. And I found that in most cases, cohorts explained it best. You know, that we were able to use cohorts to explain these different parameters of innovation. And the two that I showed here was the preferences between development and production work, and then where innovation occurs in the system in terms of collaboration.
Number two, you know, based on the limited amount of reading that I've done in this area, for example, about the NUMMI situation, it seems that in some instances there are aspects of knowledge development in which engineers did not play any significant role. So you say engineers play an essential role in all aspects of knowledge development for production workers. I mean, essential and all seem pretty strong words.
Right, yeah, this is probably a little too strong. But
Actually, I want to piggyback on that. That's why I asked the question I did and made the distinction about the relationship between what kind of engineers are coordinating the process of knowledge development with what kinds of workers for exactly those sorts of empirical reasons.
Right. Okay. Yeah, I would step back.
Bold claims, is what I'm saying.
Right, okay. Yeah, I didn't mean it to be as bold as it appears there, correct. Because it actually emphasizes that they actually only play this according to personal preference. So when they do choose to participate, they do play very important roles.
I'm thinking of this book called What Machines Can't Do by Robert Thomas. One of the fundamental points he makes in that book is that engineers often are only interested in that work which will enable them to do, quote, real engineering work, and therefore often eschew or stay away from what they regard as mundane, you know, production work on the floor.
Right.
So that kind of cultural bias might make me, you know, if he's right, that would make me skeptical that they would actually be willing to get involved with all aspects of knowledge development by production.
Right, and when I interviewed engineers, some of that did come out. But again, there was personal preferences involved where there were a significant number, I think about half the engineers are actually very interested in working with the production workers and improving.
That sounds positive.
So let's try to then look at some of the future. There are obviously a lot of different avenues we can take in this research, and one of which is to look at the effect of shifts in the production infrastructure. For instance, I suggested that there's an asymptote that limits the overall innovative ability, or the growth and overall innovative ability of production workers. So it'll be interesting to see, as this production infrastructure changes over time, how does that impact the system? We need to take a look at more complex transfers, the knowledge transfers, so that we're disaggregating now the productive ability of production workers and looking at whether these cohorts also influence the transfer of knowledge in the production system. A disaggregated analysis of engineering resources, so this would hopefully more formally answer some of the questions that have been put forth about engineers in terms of differentiating now amongst different types of innovating engineers, and what I found actually in my field study is that this whole issue of what hierarchy do you place yourself in, this engineering, this section of engineering innovation can actually impact the amount of innovation opportunities available to production workers. So this provides a very promising avenue for future research.
I want to ask you a question about that for a second, because I know that you've mentioned at least that you're interested, you've read some of the literature on legitimate peripheral participation and such, right? Okay, well there's an interesting problem there, especially if you go look at the way firms are very typically set up with regard to legitimate peripheral participation. If you believe the anthropologists and such that go for that point of view, you don't get an awful lot of learning unless you have a lot of apprenticeship, to use very bold words. Okay. But the difficulty in firms is that we have big walls between what the engineers do. Even in a model like this, where there's crosstalk, we tend to have big walls between what engineers do and what production workers do. So if you're going to have a shift, and now let's add one more thing. You've got a complicated model. I'm going to have a few assumptions here. If what you're trying to do is look at innovation as a kind of emulation of the things that engineers do, which I take you to have been saying in many ways all along here, okay, then it makes it difficult to believe, if you take that point of view about peripheral participation, that you get much transfer, you get much effect, without taking specific steps to break down those walls.
The cultural walls, right?
The cultural walls, the organizational walls, the walls that say, this is what we do over here, this is the engineering department, and that's the factory floor, so to speak.
Yeah.
There. So what is it that your research has shown you that speaks to that? And how, so let's now make me a senior manager someplace that just ask this question, raise this issue. What does your research tell you should do to break down those walls?
Maybe I can answer that question just quickly after the conclusions, or?
Well, it seems, why don't you try it here, just humor me for a second.
Okay, well, basically, from my research, AMD has done a lot of work in this area. And just simply establishing this strong culture of continuous improvement was a big battle in terms of establishing this cultural framework where, for instance, the frontline managers now have purview over the entire production process of maintenance, of engineering, and production. And because you have this one person looking over these three different functional areas, it now makes everybody work together in a more coordinated fashion. Because everybody now, the maintenance people, engineers, and production workers all depend upon each other. That there's no separate boss to go to when problems occur. That they're all in this under one boss together.
And this is due to what? This is due to the way AMD is structured?
Right, they restructured their entire organization.
Yeah.
This is not to trivialize the cultural implications at all that are involved in creating this kind of organizational restructuring. And that was just to establish now this strong culture of continuous improvement.
Right, but that doesn't sound like that's something that comes from your work, that comes from something you observed that AMD did that is consistent with some things that you believe.
Right, and what I'm going to suggest in the conclusion is that once you've built this strong culture of continuous improvement, that actually now facilitates the introduction to this model where now production workers can participate more in processes of innovation, which is the next step.
That's the short form. I'm happy to let you move on because we can
Let's
go back to
let it
that.
finish up, then we'll take our break.
Yeah,
We'll have our
exactly.
extended.
Right.
Okay, so well, I'll just skip on down to the need now for a longitudinal empirical investigation, because obviously I only looked at the system for about 4 months. I didn't follow, for instance, the progression of any particular innovation, so that's another fruitful area of future research is to now follow these innovation processes very specifically amongst a very localized group of production workers. So let's try to put our arms around this entire model and summarize and conclude. First of all, on the field study side, AMD's experience indicates that knowledge development is indeed a very long-term strategy. They've been at this continuous improvement thing for about 8-9 years. What I found is that, as I stated earlier, that continuous improvement provides the base for innovation. This model is most relevant when innovation is most compelling. That relates to our primary hypothesis. The variation in innovative ability of production workers does seem to help us to explain the sources and potential benefits of innovation in production. On the conceptual and theoretical side, or the analytical model, we found that the participation of production workers in processes of innovation can improve performance using a formal strategy of knowledge development. To do this, we first build our model of continuous improvement and innovation. We identify the production cohorts, the core, the aspirants, the reservists, and the sustainers. We define our desired migration path, that is, how do we want production workers to move through these cohorts. We allocate our expanded tasks of production, the operations, the experimentation, and the absorption, customize it to the different cohorts, while balancing this commitment to production and innovation, or continuous improvement and innovation, all according to our desired manufacturing strategy. So that concludes our talk for today, and I will turn the floor back over to the chair.
Thank you, Bill. I think we should probably take a break at this particular point. I think the custom traditionally has been after the open part of the procedure that the next part is reserved for members of the committee and such. Isn't that the practice? Yeah. Well, we respect that.
So there are 4 questions.
Yeah, are there any questions that wish to be raised from the floor before we take our break? All right, thank you very much.
Okay.
We'll
We have one question.
There's a hand
Oh, I'm
here.
sorry.
Duru,
One question.
Yes, Ken.
comparing American culture of production versus design to Japanese manufacturing culture, aren't a lot of the points you're making things that have been discovered in Japanese emphasis on better manufacturing? For example, the suggestion box in an American company is a joke.
Right.
It's like, hey, if you got an idea, just drop it in the box. It goes straight into the trash can. In Japan, they're read and acted upon. It seems like that's a logical extension of the quality revolution.
Right, and the Japanese have obviously made a lot of advances in the total quality management and this continuous improvement. But actually, even more interestingly, Japanese engineers typically are more involved on the production line than American engineers are involved on the production line. So that's, again, taking the step towards now from continuous improvement to creating more innovative abilities in the production workers.
Okay, let us reassemble here approximately 5 after 10. Okay?
You need to make a phone call.
I have to make a phone call. No longer than 10
Good luck.
Most of us may reassemble.